later. So, good morning, everybody. I'm Leonard, part of DCEL, Research Intern at DCEL, and I want us to begin. I think maybe our colleagues can catch up as we continue. So, today we're going to be looking at unsupervised learning, and I believe if you've been here since Monday, there's been a lot that has been said, and I know we're going to be encountering some, it's like a recap of what, because it's like we started from the beginning, so we are just building on top. So many things you might have heard about them, and yeah. So we're going to just try and look at them, how they work, and things like that. So we're going to start with just a bit of introduction on unsupervised learning, and then also have a look at clustering algorithms, because I think in the previous sessions that we have had, we have already mentioned this, that part of the task that unsupervised learning does is clustering, and we have different algorithms that are used for clustering. So we're going to look at this, but majorly we might focus on K-means because it's mostly used, hierarchical clustering, DB-scan, and also we look at dimensionality reduction, because I think at some point we were talking of, like, if you are dealing with a very high dimensional data, let's say 1 million by 1 million features, you might find that out of these 1 million features, some of them there might be some like correlation, because I think Cedric sometimes mentioned that, let's say if you're having feature 1, like feature 2 is just a scalar multiplied by feature 1, then feature 2 is not necessary. We can just stick with feature 1, because the information that you have in feature 1, you are just multiplying it by some sort of a scalar to get feature 2. So you find that now when you are dealing with high dimensional data, if you stick with that, it becomes computationally expensive. So we opt to reduce the dimensionality for easier computation. So for that case, in this case, we're going to be looking at PCA, principal component analysis. I think you might have used it at some point or heard about it if you haven't. I think there is another one called non-negative matrix factorization. I'll just mention a bit of it. And then as part of unsupervised learning, some of these methods can be used for anomaly detection. And I think we all understand what an anomaly is, something that is totally different from the usual one. Yeah. So some of these algorithms can be used to do the detection. So so we started by saying that if you have your data, this was in the first class when we were talking different types of machine learnings. If you have your data, if you have the corresponding labels, that sort of learning that you're going to be conducting, it's going to be supervised. But if you don't have the labels, then you're going to end up with unsupervised. And in some cases, you have a big data set, you have a portion of the labels, and the rest doesn't have. Then you may end up with stuffs like self-supervised learning. So in this case, we're going to focus on the second part where we don't have the group labels, and then from there, we ask, do you want to group your data? It ends up with clustering. And if you want to reduce the dimensionality, we end up with stuffs like PCA. So just a brief introduction. Unsupervised learning is simply a type of machine learning that learns on unlabeled data. So the main goal is to learn patterns from the data and try and group together the similarities So it's used for tasks like clustering, dimensional reduction, and yeah, it works by just identifying the patterns within your data. So why do we really need unsupervised learning? One of the reasons is we as human, let's say if we are human, if you see one sample, even if you have no idea about, you've not, let's say you come up with, let's say in terms of, let's say cars, you meet with a Jaguar. You've never seen it, you've never interacted with it, but the first time you see it, next time you see something similar to that, you'll be able to recognize that this, even though you may not know the name, but you know like this one and this one are from the same group. So when it comes to supervised learning, we as humans, we know, but now how do we tell the machine to be able to differentiate two particular items or objects without necessarily telling it that this Jaguar, this a BMW, whatever. So the main goal is now, that's why we're saying that for this type of learning, it aims at just, you give it your data, it tries and finds out the patterns within your data and try to bring together those that seems to be similar and try to separate those like based on the differences. So it tries to find like regions of high density, correlation, and or distance and bring them together. So this is just an image. We have an elephant, this is a camel, cow, but if you are giving this to, we know these are camel, but how do we tell like the models to differentiate? So it's upon the model to learn the patterns within your data and try and group them based on the patterns. So just a brief comparison between the supervised and unsupervised. So when it comes to the training data, for supervised, it's labeled. For unsupervised, it's unlabeled. The goal is for supervised is to learn to predict the target variables. I think it's been mentioned in the previous sessions, but in this case, you learn the patterns and you do the necessary. Output for the other one, we have classes or variable when it's maybe a training and the regression models, and for these we end up having, for unsupervised we end up having groups, classes, yeah. Teacher available, unsupervised, yes, you have the ground truths. These ones we don't. So typical tasks for the supervised majorly is for classification tasks and regression, and then this one we are talking of clustering and dimensionality reduction. So we're gonna now move into the clustering, and we start by asking ourselves, what's a cluster? So and this is still recap, it has been mentioned before in the first session. For a cluster, it's for a cluster, I'll term it as, it's just the normal groups that you end up with, but now the goal is to ensure that if you are having your data, here like this, and you're having another one here, the goal of clustering, what it ends up is to ensure that if you are ending up with this as one cluster and this one is as another cluster, the goal is to ensure that the similarity between this cluster, it should be very high, like we call it a high intra-cluster similarity. So the goal, like the similarity between these should be very high, and the difference between the two clusters should be very, like the difference also should be high. So what we are saying is that the closeness, the data points within a similar cluster, the distance between them should be very low. So that's what we call high intra-cluster similarity and low intercluster similarity. So these clusters should totally be different with this, but the data points inside the cluster should be close as possible. So if you are, for instance, if now you are given data points of cats and dogs, the goal is to ensure that all your data points for cats should be together, because there is a similarity between cats, like be it the colors, everything. Those are small differences, but they are very close because they are all cats. And one for dogs, also the intra-cluster similarity should be high, but now the difference in between the two clusters should be a bit higher. Yeah. So that's how we will define a cluster, and we already mentioned this. And label data based on the similarity, then discover the structure in the label data without the predefined categories, and then data points are assigned to clusters based on these similarities or distances. So we look at different types of clustering. One is hard clustering, and hard clustering simply means that there is no intersection between clusters. For instance, the example that I just drew over there, this is an example of hard clustering. What this simply means that the two classes or two classes are totally apart from each other. So there's no single point that ends up falling in both two classes. And then another type is, so the application for this is use cases for card clustering. It could be market segmentation, where maybe you are grouping your customers based on what they are interested in. So think of, let's say, you are a customer to Naivas supermarket, and there are those that are interested in stuffs, electronic stuffs, and there are those who are interested in cereals. So you may end up like, though this one may be an example for it, like in a real scenario may end up, this example it could be for a soft clustering, which we may look at into it later, because you might like both of them, so you end up falling in both clusters. So customer grouping also, and document clustering. This something in when it comes to stuff like topic modeling, where you're having a document and you may want to group it, whether it falls under, let's say, medical things or medical, or what other topics? I don't know, but I believe you get the idea. So you try to group your document based on its content. And then one limitation for hard clustering is in a situation that there is overlap between your data points. Hard clustering can never is unable to capture that, because in this case the classes are totally separate, like there's no intersection. So in a case where you're having an overlap within your data, hard clustering may not be able to capture that. So another example is soft clustering, and for soft clustering is now where we end up having an intersection. For example, in this case, if these are clusters, let's say we have a data point here, and then you're having something like this. Yeah. So you find out that this particular point falls in both classes, and it could be it may fall into this cluster based on a particular feature, and it may fall into this based on a certain feature too. Yeah. So in most cases, if I, for an example, maybe 70% falls in one class and another one 30% in another cluster. So use cases we just mentioned, in this case now we are able to capture the overlaps between clusters. And then we also have customer personas, medical diagnosis, where patients may, you go to a hospital, you do the test, and you are having symptoms that may fall in different diseases, yeah. So the benefits of soft clustering, it captures the ambiguity within your data. And then this is just an image of what I was just explaining earlier, capturing both like between hard and soft clustering. And then now we're gonna look into now the k-means algorithm. This now a method or an algorithm that is mostly used when it comes to clustering tasks. And I believe if you've worked, like you've dealt with, or you're familiar with machine learning stuffs, at some point you might have encountered a task that requires you to maybe do some clustering of your data points, and you might have bumped yourself into k-means. So we are going to look into it and maybe show some few things about it. So it helps identify the natural groupings in unlabeled data, works by grouping points based on distances to cluster centers. So yeah, used for customer segmentation, stuff like that, useful when you need structure from raw data and organized data. So let's look at how it really works. So first step is initialization. So assuming you have, I'll just draw another one, and let's say you have your data points. Like you have your data, and then you try to display your data on a 2D space, and then now you want to adopt k-means clustering on this. From what I do, how many classes do we have? Huh? 4. And what if I say that this one cluster? It could be possible too. So how k-means works is that once you have displayed your data points on a 2D space, the first thing is initialization. What does initialization mean? Is that you first start from a random centroid. Random centers, we call them centroids. So you may decide that from your data, you are picking centroids. And then there is one thing that k-mean has, and it could be a limitation, I don't know. But you have, first of all, to know the number of clusters you want. Like for instance, in this case, once you've displayed your data, I can say that, okay, I see the way it looks like it's 4 classes. So you initialize 4 centers. Or you may say, okay, I want 3 classes. Okay, let me set or initialize my k to be 3. So k stands for like the centroids. So you define it at the beginning before even running the k-means. So in this case, if I choose, I decide that my k is 3. Then I run the initialization randomly. I may choose, you may end up from your data points, you may end up having this as your first choice of centroid. You may end up having this is as another one, and you may end up having this as another centroid. So when you are doing randomly, the model doesn't, before you run it, you are just randomly choosing. So you may end up having a scenario like this. The second step, you assign all your data points to the nearest centroid. So how it works, I just mentioned earlier that it assigns points to clusters based on distances, right? Distance of a point from its centroid. So it's like you're having, let's say, your element xi, you're getting the difference between xi and some center I. So what you'll end up having is you have 3 centers, right? So you start for each and every point. For example, if you choose this, you calculate the distance between this and the first centroid. So let me put this as centroid 1, 2, 3. So this particular point distance from x1, so you find this distance, you find that particular distance, and you find that particular distance. For each and every particular point, you're finding the distance from that point to all the centers. Once you've done that, you find the point is assigned to a cluster that is closer to the point. So in this case, we'll end up this point being assigned to cluster 1. And you repeat all that for all the points. So you'll end up having, at least by the time you're finishing the loop, all the points will have been assigned to a particular center. After that, the next step, you do the updating the centroids. So for the centroids, you have already assigned all the points to a particular center. Let's say you had number of samples. Let's say it was 200. So you'll find that x1 maybe ended up having, like, let's say 70, x2 ended up having 110, and x3 ended up having what's the remainder? 20. So what we do next is to update the centers. Initial step, we did randomly, and we assigned all these points to the closest centers. Next point is we update the centers. So what we do is, for updating the centers, it's just computing the mean of all points in that particular center. So for this, you'll end up having the mean of the 70. So I think it will be computed as you do a summation of xi minus ci. So let me put xj, and then x in cluster I, this cluster I, and then j from 1 to n Then what next? I think we'll be doing sum of squares for cluster 1, K1, K equals to 1, 2, I. So we do all that, and we'll have to, once you get the new centroids, you update this. So for instance, let's say if this point, if x3 was 1, 2. So if x3, the initial center was at x3, its center was at 1, 1. If you are updating that, you may end up that maybe the new centers, you may end up having maybe, let's say, this as our x3, maybe x2 came here, and then x1 moved from here to somewhere here. So you find that the centers have already shifted. So you do that. So after updating the centroid, you continue doing the iterations until the centers at step, like the centroids at step t plus 1 is equals to centroid at step t. So like the previous step and the new step, like the centroids haven't changed, then it means that you have already reached the convergence. So no matter how many other steps you may conduct, the clusters won't change. So that's when you stop. So this is just an image of what I've been explaining over there. In data, first of all, choose randomly, assign all the data points to the closest centroid. You update the centroids. You repeat the process until there is convergence, until there's no change between clusters, like cluster 1 remains with its data points, cluster 2 remains with data points, and cluster 3, and so on. So once you read that convergence, then that's the stopping point. So advantages of this is fast and scalable, easy to interpret. It's efficient for well-separated data points. So what this really means is that, let's say, if you're having your data points, let's say something like let me put it like this, and then you're having another one like this. For k-means, in this case, it may fail to give you better classes, because from this we can clearly tell that this particular one, it may be one cluster. This one might be like the outer ring, it could be another cluster. For k-means, it may not be able to do that, but maybe if you adopt something like kernel k-means, and what kernel does, it's like this data in a 2D space, it may not be, like, you may not be able to separate the clusters to be two distinct clusters. But if you move this from a 2D space and maybe take it to a higher dimensional space, you might find that the clusters are some sort of separable. Yeah. And then sensitive to outliers. That's a disadvantage with k-means. Remember, we said for k-means, I don't think k-means can't be used for anomaly detection, Reason being, for a k-means, all the points must be assigned to a cluster. Because, for instance, if you are having this example, and you had a data point over here, this data point will be assigned to at least one class, and based on the distances, it will be assigned on this cluster, right? And remember that when you are computing your centroids, when you are updating the centroids, remember we are computing a mean across all the points that has been assigned to that particular cluster. So if you're having this and you're computing the new centroid for this, if this value is way too big, you'll end up having maybe this centroid being moved here, simply because, yes, most points are clustered over here, but this centroid will be moved away from that simply because of this one outlier. And that's one thing that it's a disadvantage for k-means. It's sensitive to that. And then I already mentioned it needs a predefined k. So in this case, I define my k equals to 3. I may choose to define my k to 4 based on what I saw. So it needs that prior to that, and then also struggles with non-convex shapes here. So one thing that people do use, and choosing the optimal k, how do we, instead of now just guessing that k equals to 3, what is the optimal value of k that we can choose? And this we use a method called an elbow method, and it simply plots the sum, the within cluster sum of squares, and in this case we are having distance between x of j in cluster I and the centroid of that particular cluster, and you are doing a summation across all the points and across all the centers. You sum all them together. So with this, there are two metrics that I use for that. So we have distortion, measures the average square distance between each data point and its assigned cluster. We've already done that. And then inertia, also the distance between the sum of square distances of each data point to its closest cluster center. So once you, like when you are running k-means, you are able to have this matrix, and then you can be able to plot it. So if you plot it, you end up with something like this. And the reason why it's called an elbow method, like it starts from the somewhere end. So as you increase the number of clusters, the value of within cluster sum of squares drops. So the idea is that once you've plotted that, once you have plotted this, the place where the elbow tries, it's like it's becoming, is it horizontal or inalala kabisa, like the change is small. That's where you can choose your optimal case. So in this case, like now the red sign, the red line, at that point you may choose, if you've plotted your data, you've run k-means, and then you plot this and you're having something like this, you may choose, okay, I want my optimal k can be 4. You end up having 4. So this one method that is used, instead of just guessing the k, you run this, and it's able to tell you what's the optimal value of k that you can choose based on your data. Next, gonna look at dbScan. Most of this I'll just maybe explain how it really works, and we'll move on. With dbScan, what it really does is that you are having your set of data, So you're having your set of data like that. Let's put some. And then you want to do clustering using dbScan. dbScan, it has some parameters that you have to set in the beginning before using it. So you have some epsilon, it's some sort of radius that you're setting. And then there is another one, minimum points that can be used to form a cluster. So if you are setting that, let's say, if you are setting epsilon to be maybe a unit of 0.5 or any value, and then or let me term it as the radius, which is simply that epsilon, and then minimum number of points, you're saying it's 4. So with dbScan, what it does is it picks one point. So it groups points as either a core point or noise. So what core point means is that if you pick this point as your core point, and then so this is your center, and then you run a circle of radius which is given by epsilon. In that circle, for that particular point, we have a minimum, like at least the predefined number of points that falls in that particular circle. So for example, if you are doing this as your center, and then you do like now that radius, and you end up having something like this. So this distance, this will be at the center, this will be a epsilon. So you find that in this case we set our points to 4. So in this particular center, do we have 4 points that fall within that circle? If at least 4 fall into it, then this particular point that we've chosen qualifies to be a core point. But for example, if you are picking this, if you are testing that these are core points, then we draw that radius across that particular point. You find that there's no particular point that falls into this. Or even if it was 1 point, but our minimum is not attained, then this particular point doesn't fit or doesn't qualify to be called a core point. So that's how dbScan does. So it tries to, for all your data points, it tries to check all the core points, and it starts drawing. So for example, if these are core point, these are core point, these are core point, these are core point, these are core point. So it will start from random. If this is a core point, and then all the points that falls into that, or all the other core points that falls into that, they're just added into that particular cluster. For example, this could be a core point. Like, okay, we have all these points have fallen into this. This was a core point on its own. But now that it falls into like the area by this, it's just added into that automatically. So you move to this as your core points. You draw a circle. It meets the number of minimum number of points. All these will end up being added to this particular cluster, and it does that iteratively. So once you have that, you might end up having, let's say, like in this data. Let me add other points over here. So you may end up having something like, okay, once you run that iteratively for all the core points, you may end up having something like this as one cluster. And all this, so in this case, you might, let me say, all this may end up having being one cluster, simply because if this is a co-point and then you are drawing everything and it meets the threshold, then all this will be added into this particular cluster. Then these ones may be termed as outliers because none of them meets the minimum number of points. This one also may end up having its own cluster. So that's how DBs can work, and it's a good method used for to do outlier detection, because all other points that don't fit in any of the clusters that are termed as noise, and this is something which could be so this is just an example that we've already explained. So you have all these forming a cluster, and then based on the number of minimum points, and then those that don't fit in any of the clusters are termed as noise. So in this case, it could be an outlier based on your data. And then we're going to look at hierarchical clustering, and this forms clusters with a tree-like structure called dendrogram that is used to do like it decides the relationships, and it maps, it joins them together based on some sort of feature. So this is just an example. So I'll move quick into this. This is just an image, and then how do we define clusters? So based on some sort of similarity, you are able to merge objects. For example, let's use the Kutz. I'm Leonard Braxton, so we may decide that each one of us over here is an individual cluster on its own. So me and Braxton, Clinton, Bartumo, we are all under D-cell, right? We can form a cluster. Some may be, let's say, in another lab origin, they form a cluster. As you continue, maybe at some point, we are all in computer science department. That can put us together as one cluster. By the end of the day, if you're doing all those based on particular features, you end up finding that at the top, all of us are part of Dekut. So this is just how like the tree forms. So you might decide later on, I'll discuss that later, but yeah. So once you have all these, like you have merged everything together and you're having this sort of a diagram, how then do we define the number of clusters? So once you've plotted this, it's upon you to decide. Like for example, in this first one, yes, you had that the first image as like now the relationships, and then you're like, okay, if I cut my tree from here, you'll end up having the whole of this as one cluster and the other one as another cluster. Is that a good thing? It's you to decide. If you are cutting it from here, you'll end up having this as one cluster, this, another one, this. So it's upon you to decide, and if you want more clusters or not. And then two types of clustering, of hierarchical clustering. One is agglomerative clustering. This it's like bottom-up approach. As I just explained, you may decide all of us, we are clusters on our own. We start merging from the bottom. Okay, we are D-cell, Origin, and other labs. We merge into clusters. We are from the same Department of Computer Science, we merge at some point. We are from School of, I don't know, you merge. At the end of the day, we are Dekut, all of us. So that is agglomerative. It's like bottom up. You are starting from individual data points as you merge, as you go up. Another one is divisive clustering. This is top down. So in that case, you'll find that we are starting from, we are all of us from Dekut. We separate ourselves based on different schools of engineering, whatever. From there, you end up, okay, maybe the course you're doing. From there, you may end up the lab that you're in until you end up you as an individual, as a standalone cluster. So those are two different approaches, and they are all used. Type of linkages with this type of clustering. We have single linkage, and what that means is that let's say data points so we say that you may decide, okay, you are starting from top down as an individual. So this, you might form this as one cluster, this cluster, this cluster. So from an individual points being a cluster, maybe based on distance, you've already formed a cluster and stuff like that. So how then do we tell, how do we start linking up different clusters as we go until we end up with one? So one is single linkage. Single linkage, it simply measures the distance between two closest points in respective clusters. So if you have these as one cluster, this is another cluster, you may tend to say, okay, I'm picking this point and computing this distance and this particular one, and with this, no, this one it would be too far. So like we choose the closest ones like that. So if this and this, let's say it was 10, I don't know, certain unit, and this one was 3. So you'll find that this class and this will first of all merge before this one. So that's single linkage. So we are using like the minimum distance between 2 points in two respective clusters. If you consider a complete linkage, measure the distance between two farthest points in two respective classes. So here we just considered like the closest one. So if you are comparing this with this cluster with this, and you are deciding to choose the complete linkage, then you'll have to compare this. And with this, maybe you may choose to compare this. So the one that with the shortest distance, you merge. Average is like average distance between all possible pairs of across two clusters. So it's like you'll be doing this, and this, every possible pairs, and you do like the average, and the one with the shortest, you merge. Word linkage is simply if you are merging this and this, what will be the within cluster variance? So the goal is to minimize. If you are adding 2 points, if it reduces the variance, well and good. But if you are adding a point to a cluster and it increases the variance, then, so it's like now in this case, you are merging those that if you add together, at least there is a reduction in variance within the cluster. So that's how word works. And then I look at now the second part. Initially I had mentioned of had mentioned of unsupervised learning being used for both clustering tasks and can also be used for now when it comes to dimensionality reduction. In this case, we already defined that if you are dealing with a high dimensional data, there could be some features which are, there is collinearity between them, that there's some relationship between the features, and then if you are working with that, then it becomes computationally expensive, assuming a million by a million matrix of, it becomes hard, and even more than that, it becomes hard when it comes to running. So the goal with dimensionality reduction is how do we reduce this data? If we are having a million features, are we able to have maybe 100,000 features that can be able to represent the variance within our data? If that is possible, then why consider a higher thing, like a very big thing, and yet you can have a smaller thing that has what the whole data contains? So that's where dimensionality reductions comes in, and in this case, we're going to look at principal component analysis, PCA. You might have come across it. And what this does, first of all, it tries to find new features from your data that are totally uncorrelated, like they are orthogonal to each other. So you know, like the property of orthogonality, like if two vectors are orthogonal to each other, if you're doing like the relationship between them, if you're doing now the dot product between them is 0, right? Yeah. So that's the whole thing of PCA. You have your big data, find new features that are totally uncorrelated, but they cover the variance of your data, like they represent your whole data. Not whole, if it's whole of your data, then it means you're keeping all the features, but you are keeping you want features that represent some sort of variance explained, yeah. And so how to choose the components is, once you have a certain number of components, they are arranged in some sort of order. First component will always cover the largest variance within your data as it goes down, yeah. So this is just an image representing that, like this, just plotted 2 dimension, and you find that like the variance explained by the PCA first, it's very large, and compared to like the second one, and you see like they are orthogonal to each other. So how do we choose the number of components? We can use a script plot. So once you have your components, you can let me just show something maybe. I think so in this I placed like various steps on how like the PCA is manually computed, though when you're implementing it, you don't like other people have already done this, but it's just some background knowledge on how it really works in the background. So first of all, we started by saying, I think it has been mentioned several times, that you have your data, first of all, is to ensure there's standardization, and you're just finding the mean of all samples. You sum all the samples, and you get that, and you get now the mean of your samples. You obtain the variance, and then to standardize, you take your x minus your x mean, and you divide by the standard deviation. And then you compute the covariance now of your standardized data. And covariance of a standardized data is simply just a dot product, and then you're dividing with the I forgot the term for this. I don't know. Yeah, but you minus n the total number of elements minus 1. Is it confidence score? There's a term for this. I don't know. Yeah. Then from there, once you've computed your covariance matrix, you compute eigenvalues and eigenvectors like that, and then by the time you finish, you end up having your eigenvectors, eigenvalues containing like the coefficient of that particular eigenvector, like the coefficient that explains the variance, and then you will have to, first of all, once you have your eigenvectors, you've already computed that and you have your eigenvectors and eigenvalues. You solve this in a, is it descending? Yes, descending order from the highest to the lowest, and this also will be sorted in the same order. Then from there, that's where now the script plot comes in on the total number of components that you want to have, because each and every vector, at least there is some variance that is explaining of your data. So you'll choose that. In this case, okay, for example, in this one, number of principal component analysis. If let's say you had, let's say if you choose 7 principal components, if you choose 7 principal components, you'll find that 90% of variance within your data is explained by 7. Or based on your data, if you're plotting, then it will be different. Maybe this was a different data. But in some cases, you can find that, let's say you've plotted that and you are finding that only 3 or 4 principal components are able to explain more than 95% of your total variance. So you find that, okay, you had 200 features or 1,000 features, and then you are doing PCA and you are like, okay, 5 principal components are able to explain 95% of variance within your data. You may opt to choose to stick with 5 and not use 1,000 features. So with this, to decide the number of components, it's also upon you to decide, okay, I want 80%. Somebody else will say, if I'm having features, principal PC components that are able to, like let's say 5 are able to explain 80% of my variance, I'm okay with that. Somebody else will say 80% is too low, I want 90% or 95%. So that's upon you to decide on which one to go for. And then advantages of PCA, multi-collinearity handling. So I started by saying that if you're having so many features, there could be some relationship between your features. But with PCA, the features that you are ending up with, that are orthogonal to each other. Like when you find the dot product between 2 vectors is 0, meaning like there's no relationship between the features that you are ending up with. So it's able to remove that. Noise reduction, it also falls under that. If there is some features which are just in your data, but they don't explain much, like let's say 0.000 something of your variance within the data. With PCA, it's able to eliminate that, because when you are ranking your features, it starts with the one that explains the highest variancy as you go down, and then you are able to choose the one that suits you. Data compression, so many features, 1 million features or 2,000 features, you end up having something like 30. So it's able to compress your data, but ensuring that at least most of the information within your data is kept. Disadvantages, interpretation, it's a challenge. For the normal features, let's say if you are having a data set of maybe age, height, stuff like that, those are your features. You are able to interpret, like if age, you just know like this an age of a person, but if you have the features of PCA, like you can't really tell like this particular component one represents whether it's age or height or income. No, you can't. Data scaling sensitivity, information loss. Yeah, if you are choosing 80% of variance explained in your data to stick with 80%, then it means that 20% of your data has, 20% of information within your data has been lost. But yeah, so that's one thing. Computational complexity can be slow and resource intensive for very large data sets. So if you're having a larger data set, then it requires some resource, because to compute like the covariance matrix for all the features, then it's, yeah, but it's helpful in a case where once you've reduced that, then it reduces the computation that is required for model training in the other things. This another one, a negative matrix factorization. This one I've just mentioned as just the equation says you are having a matrix A of an m by n. So what this does is that you are splitting your matrix into two parts, which is some, let's say, you had your matrix A is of dimension 2000 by 5000. So what this does is it's like you are trying to reduce this into a matrix of let's say W of 2000 by, let's say, 10 multiplied by another matrix of H 10 by 5000. So you find that these are two different matrices, but at least the dimension here has been reduced, and it's faster to work with this than working with a bigger one. So that's just one method for it. Can also be used now in this case in terms of dimension. It has been reduced for both. Yeah, anomaly detection. I think this will be the last thing, and I already discussed this when I was describing DB scan. K-means at least every point will be assigned to a cluster. So even if points is an outlier, at least it will be part of a cluster. But when it comes to a DB scan, all this doesn't fall in any of the clusters. So all this may be assigned to be noise, so, or an anomaly. Yeah, so that's how we do that. And then sorry, so for these things, because we are not going to have there will be no practical for this, but I already prepared some implementations, a notebook for this, and I think the link for this will be included in the materials on the website, so you can have a look at it. But it's just an implementation of all things that we've discussed from scratch, where you are defining all those mathematics that we've just done on how the different algorithms works. And in this case, I just focused on k-means and PCA. And yeah, it's for example, let me just brush through, then maybe with time, once you have access to this, you look at it. So in this case, you generated data. You have in those 3 classes, and then first of all, we started by you define a function to be computing the Euclidean distances between 2 points. It's there. Then you initialize. We said the first step was to do an initialization of the centroids, and then we are able to view them here. Those are the centroids, and then next you have to do now finding the closest clusters for each and every point. We did that, and you have that. Then you have creating clusters where now once you've done the distances between points and the closest centroid, now you have to assign a point to its closest, because for every point, let's say in this case 3 clusters, for every point you will have the distance for Euclidean distances, it will be 3. Then you pick the shortest one, and then you're assigning that particular point to the closest centroid to form a cluster. Here you find that for cluster 1 has 334 elements that has been assigned to it, set 74 to another one, 92 to another one. So I think when you'll have access to this, you'll just run and it will work out. And then this is just to see like the labels for each and every point, its label. And then you have to do update the centroids. We said you for each and every cluster, you compute the mean for that particular cluster. And then you update the centroids. So for example here, the first part, these were the initial centroids. But now after doing the assigning points to clusters, computing the centroids, you find that the new centers are different from the first ones. Then you check the convergence. Convergence simply means now you are taking like the points at stage T1 are T and T1. So when you are doing the Euclidean distance between those 2 points, it should be 0, right? If there is convergence, then it means like at iteration 2 and iteration 3, if there is convergence, then the centroid shouldn't have changed. But if they are changing, then it means they haven't converged yet. So in this case, you just checked centroids old and new centroids. You find that the values are still there, so meaning they haven't converged. And so the whole thing, when you do iteratively, at the end of the day, it will end up having 0. You have to plot, function to plot. And then now you call all those functions into one k-means, so that when you just call it, it's able to run all those. And you find, like, for example, here, this is what I was saying, like, okay, like there is some x crosses somewhere. So when you are choosing randomly, it will just pick anyhowly. And as you continue running, the centroids continue being updated until this convergency. This just I created a class. Yeah, and one thing I have to mention is that with k-means, I don't know how true this is, but with k-means, the initial centroids can affect the initial centroids that you pick or the models end up having. it could affect the clusters, how it will look like, because from how I did it up there, it separated them perfectly, right? But now after combining, I don't know where the issue went, but yeah, if you're combining that and you are now doing the random, I just placed everything in a class and in a class, K-means class, and you run. So you see something like this. You see, like the initial point, one is here, this is one, and it picked another one here, and it picked another one there. So when you are doing now the K-mean, because of those initial points, then it affects the clusters, how they will end up with. So as you continue running that, you'll find that, okay, the initial, this other one was somewhere here. But now you find that, okay, these points may be closer to this more than these ones here. So this new, it assigned this as, okay, it was, this had been assigned one cluster, that you update the centroids. So these other points, which were the whole cluster, they makes the new centroid, like the center, to come here. So once it comes here, you find that all these other ones, they are far away from this. So you'll find that by the end of the day, all this, it will stick to be one cluster. And hizo zingine zitafaitia huko chini. And that's one thing that maybe K-mean has. So you start with the wrong place, then it affects the line. So in this case, it ran, and then until there was no changes in the centroids. So you end up having this as one cluster, and then hizi zingine huku chini zina split. So yeah. And then also I looked at PCA dimensional reduction, and here just looked at just the iris dataset, and then we did that, and you have the covariance matrix, and then now we do implementations of PCA the way we have stated it. You start by standardizing the data. We define the function for means, standard deviation, and then you standardize it. From there, you compute the covariance matrix. You did that. Compute the eigenvectors. We compute. So this is where I was saying that once you have computed the eigenvalues and eigenvectors, you sort them in ascending or descending from the top to the least. So you have this as it goes down, as the value reduces, and then you choose the number of components that you want. So if you are sticking with that, so I just mentioned there is one here where now the variance explained by each PC. So the first one, we said always the first one will be the one capturing the highest variance within your data, and then the other one, like the value reduces as it goes. So you find that the first one, 72% of your data is explained by the first principal component. The second one explains 22%, the third one 3%, the fourth one explains 0.52 as it goes. So if you're having so many, that number will be reducing like that. Then now you can plot the cumulative ones and cumulative script plot, and then you are able to choose what size or what percentage of variance that you want to stick with. So if you're plotting this, you're like, okay, if I choose 3 principal components, I'm like, I don't know, 3 principal components, it gives you like 99.48% of your data. So you don't have to keep all the other, but yeah, 95, if you want to just stick with 2, you may decide, okay, let me stick with 95%. So yeah, so this is how it works. And then once you choose, you have that, now you take that projection matrix, you multiply with your data to project, so to end up having new set of the data, and then you are able to visualize it here. And then also with PCA, we just did now another one now where you are using sklearn and see if what we've implemented from scratch is the same as what the scikit-learn is saying. So we did that. You call PCA, number of components, and then standardize everything. The plot is the same, meaning like the implementation, like all those things that we've done is correct. And then also for this case, if you're doing the projection, similar thing. So meaning, yeah. So that's exactly how it works. So most of these packages that we use is just, there are some maths behind it that have already been done and placed in some sort of a library. So when you're doing now your implementation, you don't have to define everything, but at least you understand what's working in the background. Yeah, this just placing in a class. Yeah, that's it from me. Maybe any other question? If there is none, thank you for listening. Any question? Okay. Yeah, I think it's just a matter of trial and error, because the main goal we say that it's for clusters, different clusters, is just to ensure like the within cluster some square. It's more. So if you see there is an outlier, and maybe, because another thing is like maybe you may not want to end up having so many other classes. So now that's something upon you also to decide. Even with this, here it's picking 4, like the person is picking 4. You may decide, okay, I don't want 4, I want 3, because that's where the step stops. Or another person will like, okay, I go for 5. So also the method is just to give you a baseline. Yeah, it's to give you a baseline, and it's you now to define what you really want. Yes. Yeah. I don't think so. I don't think so, unless the questions that are being asked before are the same. Like I think maybe I'll consider, let's say, for example, Yes. Yeah, the number of questions that you ask, yes, it separates that. But the only scenario that I would say maybe that could lead to both cases giving you same plots and same classes, like even at every stage where they are joining is the same. I think, let's say, maybe for top down, you started maybe asking, let's say we have maybe some x1, x2, x3, x4, x5, right? Maybe these are set of questions that you're asking. From top down, if you started from x1 as you move to x2, and you end up with that plot, from bottom up, if you start with x5 as you go like this, x5, x4, x3, x3, x2, x1, you may end up with 1. But if maybe now when coming back, maybe you started with x4 and then x5 or x1, x2. In this case, if you change, then I think you might end up having 2 different classes. But if you are maintaining the order down and you retain the same, I think you should end up with the same. So maybe that's something that the model itself has to. And just thinking of what Emerson was explaining yesterday, maybe for decision trees, I don't know if it's the same for this, where maybe it evaluates what to ask, what's important. If this adds more value, then this one will be given the first priority. Yeah, I think those are things that maybe the model may. Yeah. Okay, thank you.